All right, so today we're going to start with section 9.2, and we're going to be looking at kind of a continuation of what we did last time. We talked about probabilities last time, and I mentioned that these were like single event, like single outcome, one time we did this scenario, whatever, and that today we're going to do something repetitive. So in order to talk about experiments and to keep our thoughts organized, one of the ways we're going to do that is to use tree diagrams. So a tree diagram is simply a sample space model where each outcome is designated by a separate branch. So what we did last time could be thought of as one-stage experiments. The experiments are over after one step, right? So like you had one single die and you rolled it one time, experiment over. So you're playing the lottery and you pull out one, or like some kind of a raffle would be a better example, a raffle, and you pulled out one ticket and the game is over, that person wins and we're done. A two-stage experiment, which we're going to be working on those and then further as well today, are experiments that are over after two steps, or if you did 3 steps or 4 steps, if you were doing a 3 or 4 step experiment. So it has 2 sets of branches. So I want you to think about actually let me do a head-tail coin because it's easier to draw and I don't have much space at the bottom of this one. So imagine that I have a coin and there's 2 outcomes, right? It can be heads or it can be tails. So if I were to draw a tree diagram to represent this, it looks like this, where one outcome is heads, the other outcome is tails. And along each of the branches, I write the probability. Well, with a coin, it's a 1/2 probability of, tossing a heads, or landing on heads, and 1/2 possibility that it lands on tails. If you did it a second time, what happens is you have that same set of tree branches. So now I want to flip the coin twice. So the first time I flipped the coin, I could get a head or a tail. And then I do a second set of branches extending off of that outcome. So no matter what that outcome is, I do it again. And when I do that, I get again a head or a tail each time. And this would be a 2-step tree diagram. And then along each branch, I write the probability of each outcome. So the first outcomes was a 1/2. And then if I tossed a heads, I do it again, and then I still get a head or a tail, but it's still a 1/2 probability each time. And if I toss the tails, I flip the coin again, and again happens to be equally likely, 1/2 probability each time. And if I wanted to, along this tree diagram, I could find the probability of rolling or flipping, in this case, 2 heads, by simply multiplying along the branches that have the 2 heads on them. Okay, and we're going to show up on the next multiplication rule. That's the next slide. So this organizes my data. It's not the only way to organize this particular information, but it's a pretty universal one. It works in most cases really nicely. And we will see another option for some situations too, but the tree diagram is a good one. So if we use this tree diagram idea, there is a multiplication rule that I just mentioned. So for all multi-stage experiments, the probability of an outcome along any path of the tree diagram is equal to the product of the probabilities along the path. And it's all that it's saying is that you just take a branch and you multiply the numbers that are along that branch. Whatever the probabilities are that are along that branch, you multiply them, and that's the probability of getting that branch of that outcome. And there's like this note. It's a nice reminder note. Maybe it's a warning note. I don't know. But it's telling you, please, you're going to do a tree diagram or something equivalent on every single probability problem. It's a practice thing, right? So we're going to practice doing tree diagrams. Some of them you're going to be like, I don't really need to do one in order to find the answer. I can reason through it. Great. But I want you to practice so that when the hard ones come up, that you can't do it without a tree diagram, you're very familiar with the process, and it's easy to do the tree diagram to find the answer. So tree diagrams are something equivalent we shown on every single problem. Make sure you allow yourself space. So sometimes I know that when we don't know how to do a problem, you kind of skip some space and you move on. you need to skip maybe more space than you normally would. It's going to take a little bit of space to do a tree diagram, right? These pictures, I even drew ones specifically that were small, already took up a pretty decent amount of space. Imagine if I did my dice example and there weren't 2 outcomes, there were 6 outcomes. So instead of 2 branches out here, it says heads and tails, I have 6 of them that says 1, 2, 3, 4, 5, and 6. The pictures get big very quickly, the more outcomes that are happening. All right, a couple more things and then we're going to do an example. Independent events. Independent events are events in which the occurrence of one event has no influence on the outcome of a second event. So maybe it's because the events have absolutely nothing in common, right? Like you're flipping a coin and you're tossing a dice. Well, clearly there's no relationship between what the coin says and what the die says, right? Those would be independent events. But even the heads itself, the coin itself, from one flip to the next flip, there's no bearing on the first flip to the second flip, right? Has absolutely nothing, the second flip has absolutely nothing to do with what the first flip was. They're independent events. The outcome of one does not affect the outcome of the other. Now, this is not the same as mutually exclusive events. We talked about that last time, and independent and mutually exclusive are different things, but they're often confused when I ask students about them because they feel like they're somehow related. Mutually exclusive means the events can't happen at the same time, right? I can't flip heads and flip tails. It's one or the other, right? And in fact, in a single flip, the outcome of one does affect the outcome of the other. Like I can't have both those outcomes occurring. But if you were talking about independent events, you're talking about the event itself, not the outcomes, right? Mutually exclusive is the outcomes of the events having nothing in common. Independent is the events themselves don't have anything to do with each other, right? The flipping the coin one time and then flipping the coin the second time don't affect one another. We're going to see an example where things do get affected, and so you can see how that plays into it when we do example 1. If you have independent events and you want to know the probability that both events occur, it's just the multiplication of the 2 events' individual probabilities. So the probability of event 1, the probability of event 2, you multiply them together, and that's the probability that both events happen. Right? So over here, if I wanted to know the probability of getting heads, I multiply the probability of getting heads times the probability again of getting heads, and that's the probability of getting 2 heads in a row. 1/4, 1/2 times 1/2 is 1/4. Okay, this one is an example of one that are not independent events. So we've got an executive committee of 10 members. So there's 10 people on a committee. 4 of them are women and 6 are men. And we're going to select 3 of them to go to Hawaii. Now, once we select one person, there's no longer 10 people to select from, right? So therefore, the probabilities change on the second person being selected. And whether that person selected first was a male or a female affects the probability of the second selection. So the outcomes here are not, or the events here, the event of selecting our individual people, are not independent events. They do affect each other. And you see that happening when we create our tree diagram. So in this tree diagram, what we're going to be concerned with is not the individual people, but the category, the way they're being described. So if you take a look at the next page, you can see what I mean. The questions that were asked on the next page is the probability of the women or the men being selected, right? Not the individual people. It's not about the individual people. It's about whether it's a male or a female. So when we're looking at this and we're creating our tree diagram, that's the categories that we're describing, male and female, or man and woman, however you want to describe it. So over here, we've got, it's described here as men and women, so I'll go with that. So we're going to do man here, and we're going to do woman here. So I've got, imagine having, like all their names thrown into a bag, right? So like we're drawing one out. So I reach into the bag and I pick out a name. What is the probability that the name that I pick out is a man's name? Or that the name belongs to a man? 6 out of 10. There are 6 men and there are 10 people total. It's a 6 out of 10 probability that when I reach into the bag, I select the name of a man. So what's the probability that it's a woman's name? 4 out of 10. And what I'd like you to notice is that along this branch, right, this branches set right here, they add up to 1. And that will always happen. Along each set of branches, they add up to 1. In fact, it happened over here too, right? Along each set of branches, it adds up to 1, right? This adds up to 1. Oops, this one adds up to 1. All of them have that probability, or that property, excuse me. Okay, so after I select one person's name, I'm not done with this experiment. It's not one person gets to go to Hawaii, it's 3 people get to go to Hawaii, right? So after I select person number 1, I have to do another set of branches to select person number 2. And again, there are 2 options. It's a man or it's a woman. But it's not 6/10 and 4/10 along those branches again, right? Whoever was selected has already been selected. Their name is no longer in the basket of names. How many names are in the basket of names now? 9, right? 9 of them are in there. So all of these probabilities are going to be out of 9 because there's only 9 people left to select from. So whatever happens next, it's out of 9 instead of out of 10. Now the numerators will depend on who was selected first. So if we're along the first top, like the top branch, it means there's a man already going. His name is no longer in the basket. So how many men's names are still in the basket? 5, because I already pulled one of them out. So there are 5 men's names now in the men names in the basket. How many women's names are in the basket? 4, the same 4 that were originally there, right? The probabilities changed because these are not independent events. Along this branch at the bottom, I've selected a woman. So if I've selected a woman along this branch, how many men's names are still left in the basket? 6. And how many women's names are? 3. But again, do you see? 6 and 9, 3 and 9 add to 1. 5 and 9, 4 and 9, they add to 1. Now I have 2 people that have been selected. I still don't know who they are, but I have 2 people who've been selected to go to Hawaii, and I'm supposed to have 3. So I need to do it one more time. So I do one more set of branches. Okay, so a little bit of tips. If you're feeling like, oh my goodness, everything's running into each other, if you make your branches longer, you give yourself more space. Okay, so just sort of an organizational tip. Make the branches longer and you give yourself some more space to write things out. If you don't like writing the branches, like your tree diagrams from left to right, you can also write them from top to bottom. So you could have drawn the picture, I don't have space on this one, but you could have drawn the picture like this and then drawn your branches down like this. Okay, that's another way to do it. It's the same picture, it's just drawn, top down instead of left to right. Okay, so over here, I still have man and woman along each of the different branches, MWs. But now it depends on the previous 2, picks of names on my probabilities. But one thing is the same for all of them. It's how many names are in the basket. How many names are in the basket right now? 8. So every denominator along this pair of, this last 6 set of eight of these branches right over here is going to have a denominator of 8. All right, so let's go along the top. If I go along the top, strictly along the straight across the top, I've selected 2 men. How many men's names are left if I've selected 2 men? 4 out of 8. So how many women's names are left?
4.
The same 4 because none of them have been selected out of 8, right? Along the second branch here, I've had 1 man's name and 1 woman's name that has been selected. 1 of each have been picked. So how many men are left in the basket at that point? 5 out of 8. And how many women are left? 3 out of 8. Again, adding up to 1. Along this branch, I have a woman and then a man. I selected in different order, but it's actually the same thing as selecting man-woman as selecting woman-man. I still have the 5/8 and the 3/8, right? There's still 5 names that are men, 3 names that are women. Okay, on the bottom here, I've selected 2 women. So I've selected 2 women. How many men are left in the basket? The same as 6 that started with, out of 8. And how many women are left in the basket? 2. So this is the complete diagram, tree diagram for this scenario. Okay, The diagram itself is the time-consuming part. Answering the questions is not. So we're about to answer some questions about these. But is the diagram okay? All right, so let's look at the questions that are posed about this scenario now. The first one asks the probability that all three selected are women. What is it asking me to find from this diagram? Yeah, the product of the very last branch, right? I'm going to highlight it, yeah. This is the only tree branch that gives me 3 women going to Hawaii, correct? And the multiplication theorem over here said that what I need to do to find those probabilities is multiply the individual probabilities together. So I need to multiply 4/10, 3/9, and 2/8. Do you have a question, Cora?
I'm gonna wait.
Okay.
Oh, hang on.
You're good now. Okay, no problem. All right, so we said we had, what was our numbers? 4/10, 3/9, and 2/8. We've already worked with multiplication of fractions. You're certainly welcome to multiply straight across and multiply straight. You can do that and then reduce everything, but we could also reduce in the middle of it. And so I think it's helpful to do so. For example, the 4 and the 10 at the beginning both divide by 2. So if I divide 4 by 2, I get 2, and 10 by 2, I get 5. 3 and 9 both divide by 3. So 3 divided by 3 is 1, and 9 divided by 3 is 3. Same thing for 2 and 8. 2 and 8 both divide by 2. So 2 divided by 2 is 1, and 8 divided by 2 is 4. If you want to multiply across the straight top and bottom now, it's pretty nice. We'll still have a little bit of reducing at the end, but not too much. 2 times 1 times 1 is 2. And then 5 times 3 times 4 is what? 60. 2 out of 60 is still not quite reduced. Yeah, I need to divide them both by 2, right? And so 2 divided by 2 is 1, and 60 divided by 2 is 30. A 1 out of 30 chance that all 3 people going are women. It's not very high, right? It's not very high, 1 out of 30. Part B, however, asks a question that we can find in 2 different ways. Part B says, what's the probability at least 1 man goes? So it's asking for the probability that 1 man, 2 men, or all 3 are men that are going, right? So one way to do that, this is not the way we're going to, by the way, but one way to do that would be to find the probability that 1 man goes, plus the probability that 2 men go, plus the probability of 3 men going. But there's an easier way to do that. What is the only thing that you can't have and satisfy that question? All women going, right? So I'm supposed to have not all women. And one of the things that we learned last time is that if I want the probability of not all women, that's exactly 1 minus the probability of having all women. And I already calculated having all women. That was part A. It was 1 out of 30. So what do I get if I take 1 minus 1 out of 30?
29/38.
Yeah, it's 29 out of 30. Right? Get a common denominator, subtract if you wish. But it's 29 out of 30 that are missing. It's very likely that at least 1 man gets to go on this trip. Now, it's also pretty likely that at least 1 woman gets to go, just not all women going, right? Now, if you were to try to do this, whoops, sorry about that, this piece right here, let me go back to our tree diagram to show you what you would have to actually do and why that's not particularly friendly. In order to get all men going, it's the top branch, just like all women going, right? I can multiply those out, that's no problem. But if I want to get 2 men going, I have to find all the branches that have 2 men on it. Well, this is 2 men, and this one's 2 men, and this one's 2 men. And I'd need those probabilities, and then I'd have to add them together. So I'd have to do 3 multiplication pieces, right? Multiply along 3 different branches, and I'd have to add those 3 branches together. That's 2 men going. And then 1 man going would be this one, and this one, and this one. Again, 3 multiplications, and then I'd add them all together. Okay? Obviously, at this point, I've highlighted everything in the diagram. I get that. But that's just it. I'd have to find 7 different multiplications, and I'd have to add them all together if I wanted to do what's circled in red. That's a lot of work. So looking for a complements principle, like we ended up doing, is a very helpful step. Okay, let's do another example. We could do a tree diagram on this, but I also want to show you places where tree diagrams you have another option besides just a tree diagram, and this is a good one to do that. All right, so instead of our box containing people's names, we've got a box that contains slips of paper. The slips of paper are numbered 4, 6, 7, 8, and 9. And a player reaches into the box and draws out 2 slips of paper. So you can say they draw the 2 slips out at one time, or you could say they draw out 1 slip, hang on to it, and then they draw out a second slip. It doesn't make any difference. The process works the same. Either way, they have 2 distinctly different pieces of paper. Much like we would have to do over here, we have 2 distinctly different people going, or in this case, 3 distinctly different people going to Hawaii. Okay? Now, after they do that, they're going to add them together, the 2 slips of paper. And when they add the 2 slips of paper together, they're going to decide, did I get an even number or did I get an odd number? Okay, everybody good so far? Okay. So one option is that we could actually draw out a tree diagram, and we could write out that we have a 4, 6, 8, 9, and 4, 6, 7, 8, and 9. So let me actually show you what it would look like with a tree diagram. Don't do that because I'm going to erase it in just a second. But we would do, 4, 6, 7, 8, and 9. And then off of each of those, we would write down the options of things that are still available. Okay? It'd be a pretty big tree diagram, wouldn't it? It'd be kind of messy. So instead, what we can do, as another option here, is we can write down all the things that could be drawn. We're just going to make a list. So if I draw the number 4 as my first draw, what else could I draw? Okay, I can't draw the 4 again, right? 4 and what? 4 and 6. So I'm just going to write them beside each other. Or I could draw 4 and 7. Or I could draw 4 and 8. I think I have one more, right? 4 and 9. Yeah. We're just going to list it over here. Maybe it would be better if they were listed in order, like all bunched together, but that's okay. 4 and 9. That is every possible thing that I can combine with a 4, right? Where I'm reaching in, I'm drawing 2 numbers out. I could draw a 4, 6, a 4, 7, a 4, 8, a 4, 9. But maybe I don't draw a 4. Fine. I can draw a 5. I can't draw a 5. There's not a 5 in the bucket. There's a 6, right? 6. I could draw a 6. Okay, good. But I already wrote down the 4 and the 6 option, so I don't need to write it again. I could draw out a 6 and a 7, or a 6 and a 8, or a 6 and a 9. That's all the ways that I can draw a 6, because I've already got the 6, 4 listed up there, right? Okay. So maybe I don't draw a 4 and I don't draw a 6, so what else could I draw? 7 and 8, or 7 and 9, and 8 and 9. And these are all my different options, and they're all equally likely because there's exactly one of them all, of each of them in the basket of numbers. Okay. Now, the question has to do with the winning, and winning has to do with if the sum, right, that's addition, is even. So I'm going to highlight, maybe you can circle if you'd like, but I would try to make it not too over the top because we're going to change the process here in just a second. We'd like to know which of these are even. So when I add 4 and 6 together, do I get an even number? I do. How about when I add 4 and 7? No. How about when I add 4 and 8? Yes. 4 and 9? No. 6 and 7? No. 6 and 8? Yes. Yeah, it's okay. 6 and 9? No. 7 and 8? No. 7 and 9. Oh, I was supposed to be looking for odds, wasn't I? It's okay. I've highlighted evens. We'll keep going with it. 7 and 9, is that even? Yes. Okay. And 8 and 9. No. Okay. So the yellow ones that I highlighted are actually losers, right? No, I did it right. I did. I'm sorry. I read it on the screen wrong. I highlighted the ones that are winners. I did. Yes. Okay, cool. So how many of them were winners? 4. Out of how many different outcomes possible? 10. There are 10 options? Cool. And this reduces to 2/5. So with the setup the way that it is a 2/5 probability of winning. Yes, ma'am?
So you said earlier that you want us to always draw the tree diagrams, but this one you said we don't have to. When do we know when we need to and when we don't need to?
Okay, so what I'm showing you is another option for this one. A tree diagram would have worked just fine. There'd be no problem with doing a tree diagram here. This is just another option on this one. So if you take a look back, it actually says a tree diagram or something equivalent.
Okay.
This is the something equivalent that would be an option here. So sometimes a tree diagram is just really like the options, the best way to do it. This is a good one who we're here to do a tree diagram on it because I don't know the people's individual names. Here I actually have the list of individual numbers. And so here it kind of makes more sense to actually write them out this way. And if I were to write them out this way in a tree diagram, it would be a very big and bulky tree diagram, which maybe makes it less desirable. Yeah. What if we didn't add, we multiplied? I'm going to change colors. I'm going to win now if I get an even number when they're multiplied, not when they're added. So, is 4 times 6 even? 4 times 7? 4 times 8? Hope you're not really multiplying them. How do you know if a number is going to be even when you're multiplying? If one of the original numbers was even, right? So most of these are even, right? Because if I'm multiplying by something even, I'm getting something even. 4 and 9 is even because 4 is even. 6 and 7, evens because 6 is even. 6 and 8, even. Everything except 7 and 9, right? So if I do multiplication instead, what is the likelihood I win the game? 9 out of 10. Right? So does the numbers multiplied change? The answer is, of course, yes, it changes. And it changes to 9 out of 10 instead of 4 out of 10, which was 2 out of 5. Oh, I didn't get all the way over there. Thank you. You're right. Whoops. There we go. All right, so the red ones are evens multiplied. Okay, does that make sense? All right, so a tree diagram still would have worked. It just would have been a little bit bulkier on this one. Okay, let's take a look at one more. I think we have time for my spinner question, and then we'll stop for today. Suppose an experiment consists of spinning the first spinner, followed by the second spinner. Part A wants us to write the sample space for the outcomes. So sample space really is just a collection of all outcomes. So when I spin the first spinner, I can get a 1, right? That's one of my outcomes on the first spinner. And then I follow it with a spinner on the second spinner. I'm going to write them like they're ordered pairs. You could just write them as like digits, and that would be fine too. So I'm going to do mine like this. But I could spin 1 on the first spinner, and I could spin a 1 on the second spinner. I could spin a 1 on the first spinner and a 2 on the second spinner, or a 1 on the first spinner and a 3 on the second spinner. Or I could do a 2 on the first spinner with a 1 on the second, 2 on the first and 2 on the second, 2 on the first and 3 on the second. This is my sample space. And because the spinners are dividing the shapes into equal regions, right? The first one's in half, the second one's in thirds. These are all equally likely outcomes, okay? It's kind of like over here. They're all in the basket one time. I don't have 2 4s in there, so they're equally likely to occur, okay? So these are equally likely outcomes as well. So we can take a look. This is one where, because I've written out the sample space, I don't really need a tree diagram to do this either, okay? This is sort of the work that's going with it, and they asked me to do it anyway for part A. So when we look at part B, we can calculate this pretty nicely. What is the probability of spinning two even numbers? So where do you see two even numbers? 2, 2. And it's the only one, right? So there's one of those compared to how many outcomes total? 6. So it's 1 out of 6. What does the phrase at least one mean? Minimum of 1. So in our case, it means 1 or 2, right? I have 1 or 2 2s in the values. So where do you see at least 1 2? 1 2, 2 1, 2 2, 2 3. There's 4 places that have at least one of the outcomes coming up as a 2. So there are 4 of them out of 6, which reduces to 2/3. We will reduce our probabilities every single time, okay? The last one says exactly 1 2. So here's exactly 1 2. Here's exactly 1. And here's exactly 1. I leave out the 2 2 option. So like you just said, there are 3 of those out of 6, which gives me 1/2. And we will pause there for today.